Anyone is having any specific doubt from the assignment? Good afternoon. Are you able to hear me? Okay. So let us start. Let other people join maybe in 1 or 2 minutes. So, uh, welcome everyone to the live lecture for the course Engineering Drawing and Computer Graphics. So this is being conducted by Professor Rajaram Lakkaraju from IIT Kharagpur, and I'm Sanika. I'm a PhD student in IISc Bangalore, and I will be conducting this live lecture. So in this live lecture, in this live lecture, we will see the projection of lines and planes. So this will be approximately a 1 hour lecture conducted so that you can discuss your doubts, and I will also solve some problems and discuss the concepts. So last time, I have already uploaded the last time lecture on YouTube, so you can watch that also. So I will quickly go through what we did last time. So last time we saw uh, how will the projections of line look when they were inclined to the vertical plane, horizontal plane, and how they will change as we change the angle. So let us again imagine a line AB that is inclined to the horizontal plane by an angle of 30 degrees. So, if I keep the angle with the horizontal plane constant and change my angle with the vertical plane, I'm going to be tracing a cone which is similar to this cone that I have shown here, similar to this cone. So, if I have my point A here, which let us fix at 30 above HP and 40 in front of VP. So if I have this A over here, then the point B is going to trace this circle. So given that the line is making 30 degrees with the horizontal plane, the line can now be anywhere on this vertical cone. So B point will be tracing the circle of the cone that I'm showing on the slides. So if we try to trace this position of B in the horizontal plane, then since it is making angle with HB, I'm going to trace a circle in the horizontal plane. Whereas, since I'm not changing the angle with the HP anywhere I go, this height is going to stay constant. So, in horizontal plane, I will trace a circle, and in vertical plane, if I see, I will be tracing a line. So, as I go here like this anti-clockwise, I will move from the B point. So A point will be here, which is 30 above HP. So that 30 will be seen in the vertical plane, and it is 40 in front of VP. So this distance will be 40. So I have fixed the point A here. This is 30 degrees angle, making an angle of 30 degrees with the horizontal plane. So angle with the horizontal plane is always seen in the vertical plane. So now as I move along this arrow in anti-clockwise direction, I will start here. My B point will go here. It will come back here. It will go here, and it will come back here as I move along this arrow. So as long as I do not change the inclination of the line with respect to the horizontal plane, the elevation or height of the point B is not going to change. It will remain constant. So given that this angle is 30, my point is going to lie on this line that I'm marking with red. So this height will always be constant, which will be equal to L sine 30 in this case. So this is the angle 30. So this will be the length of line sine of 30. So that will always remain constant. So this point B will trace a line in vertical plane. And as long as I'm not changing the angle with the horizontal plane, the length of the projection in the horizontal plane will not change. So I had showed this model last time that if I'm keeping it like this, here, and I'm rotating this. So this is my line AB, which I'm rotating. So my angle with respect to the horizontal plane, this angle, this one, is constant. So if I see from the top, I'm going to trace a circle with radius of L cos 30, which will be constant wherever I go. So as long as I keep the angle constant, my this distance angle with HP constant, my distance in vertical plane will remain constant, and the radius of the projection will remain constant. Now, uh, to conclude this slide, circle is the locus of all points B when line AB makes true angle 30 degrees with the horizontal plane. So angle with HP is always 30 degrees, but as you move along, if let's say I have, instead of the line being parallel to VP, which is currently this case here, this position is when the line is parallel to VP. In case it is not parallel to VP, the point B will be somewhere here. So the angle, this angle, this angle that we see is more than 30, whereas since my B point is still here, the actual angle, the true angle with HP has still not changed. So circle is the locus of all points B when line AB makes true angle 30 degrees with HP, or any true angle which is a constant with respect to HP. And in VP, this line will be the locus of all points B when line AB makes true angle, a constant true angle. Here we have taken it as 30 degrees with HP. So when do you see the true length and the true angle? So true length and true angle with respect to HP will only be visible in a plane that is so this is the horizontal plane. The true angle will be visible in a plane which satisfies two conditions. It is perpendicular to the horizontal plane, so this is the horizontal plane, so the plane should be vertical here, and that plane passes through the line that we are considering. So if I'm having an angle like this and I have a plane like this, then this will represent a true angle. As soon as I rotate it like this plane no longer shows the true angle of this line with respect to HP. So I will have to have a plane which rotates with the line in order to see the true angle at all times. So when we say that I have a true angle of 30 degrees and then I rotate it here, special case is that VP becomes that plane which is also perpendicular to the horizontal plane and passing through the line when this line is parallel to the vertical plane. So, and only in that case we see the true angle and the true length as well. So now consider that first we were considering line is inclined to HP. Now consider that here there is a imaginary plane, imagine, and I have uh, first placed it parallel to VP. Now I am saying that it is inclined to VP here or here, somewhere it is inclined to VP. Now what was the first condition I put? It is inclined to HP 30 degrees and wait. So my vertical plane is here, horizontal plane is here. So right now it is parallel to VP and it is inclined to the horizontal plane like this. If I am again making it at an angle to the vertical plane, what happens? Right now I was parallel to the vertical plane, so this was how the line was looking. So I had angle with the horizontal plane which was visible in the vertical plane. This is 30. Alright. And uh, my projection is looking like this in the horizontal plane. So when I start rotating this point B is going to trace the circle, the yellow circle, and my angle with vertical plane is going to change. So let us say I have rotated it here from here to here. Now the corresponding point in the front view is, so this was our locus where the point B should be always at a constant height because I'm not changing the angle. So this is my point B. This is my point B. This was our A. This was our initial B. Now let us call this point B1 and B1. So AB1 is my new projection after I have rotated it also in VP. So now whatever angle I see here, this is my A and this is my B. So the angle with respect to, in the horizontal plane, I see the angle with respect to VP. But again I like to remind you that when do we see the true angle with VP or true angle with any plane? When, so we are considering true angle with respect to the vertical plane, so that plane should be perpendicular to the vertical plane. So horizontal plane is one such plane which is perpendicular to the vertical plane. But since I have already rotated the line like this, also have to rotate this perpendicular plane with that angle so that I see the true angle with respect to VP. But in this case, I already said that if I want to see the angle with respect to VP, I need this line to be parallel to the horizontal plane. But when I started, I had already tilted it 30 degrees with respect to HP and then tilted with respect to VP. So whatever angle I see here in this figure is not the true angle with respect to the vertical plane. So uh, here I will just remind you that when I am having a constant angle with respect to horizontal plane, I trace a circle in the horizontal plane and a line in the vertical plane. Now, instead of horizontal plane, if I have a constant angle with respect to the vertical plane, here like this, so this is my vertical plane and I have a constant angle with this vertical plane. So this pencil can rotate anyhow, so this is now going to trace a horizontal cone and it will trace a circle in the vertical plane. And since it is moving like this and I'm not changing the angle with respect to VP, I'm not changing this angle that I can see in the top view with respect to VP. This point B again, so this is my point A, here the center of the circle, and point B is going to trace this circle. So, and this is point A, and point B is going to trace along this line in the horizontal plane. So now here in case in the case where we have a constant angle with respect to vertical plane, we have a we have the locus of B as a circle in vertical plane and the locus of B as a straight line in the horizontal plane. So if we compare both here, uh, this is the locus of all points B in the horizontal plane, such that this is A and this is locus of all points B, such that it makes a constant angle with respect to the horizontal plane, and this is A and this is B. So this line is now locus of all points B, which um, of lines such that they make a constant angle 30 degrees with respect to the horizontal plane. And similarly here, uh, if I have a line in in that has a constant angle with respect to the vertical plane, then it will trace the all points B such that the line AB makes angle of 45 degrees with the vertical plane. We'll trace a circle this whose radius will be L cos 45, and here my height will be L sin 45. Similarly, over here this will be L cos 30. This, if you see this triangle, this is my length and this is 30. So L cos 30, and this height will be L sin 30. So now in the lectures you solved a problem which said that line AB is 20 mm long. It is inclined at 30 degrees and 45 degrees to horizontal plane and vertical plane respectively. So when you say that the line makes an angle with HP or VP, it is the true angle. When you say the front view makes an angle, or when you say the top view makes an angle, it is a apparent angle. So here both the angles that are given are the true angles. So what we are going to do now is, here they have mentioned that point A is 30 mm above HP. So above HP, that will be seen in the vertical plane. So let us mark a point here A. This distance will be 30, and this point A is 40 mm in front of VP. So that distance will be seen in the horizontal plane. So let us mark that point here. So this is A dash, which is 40 mm. So we have located the point A. Now what they have told is line AB is 20 mm long. So 20 mm is the true length of this line, and we have the true angles. So now what is the true angle with respect to HP? True angle with respect to HP is equal to 30 degrees. So I have 30 degrees with respect to HP and I have true length. So with this, I can only get the locus of point B. So this is my point A. I know that when my line is in parallel to VP, when my line is parallel to VP, I will see your true length and I can see the true angle. So after I draw this, I draw such a line which is at 30 degrees and whose length is 20 mm. I get this point, which is now the height of the point B from point A. So this is the height of the cone. So wherever I rotate this pencil now, this point B will be along this line. So by doing this, we actually got a locus of this point B. Okay. And similarly, since this is at 30 degrees, this line will get projected here and this will be the projected line. So if I have tilted it with respect to HP here, if I have tilted with respect to HP here, this is the projected length that is falling here, and even if I rotate this projected length will be constant. So now uh, this was one locus of B that I got, and this circle will be the another locus of B that I will get, locus of B. So both of these are that I've drawn in red are the locus of point B of lines such that they are inclined at 30 degrees with respect to the horizontal plane. Now I will change the color. Let us go for green. Yeah, so the second condition is that this line AB is at 45 degrees with respect to the vertical plane. So the angle with respect to the vertical plane is seen in the horizontal plane in top view. So uh, let us have a XY plane here. So to avoid confusion, I'm drawing it here. But this point A, when you actually draw it, you should draw it together. Oh, sorry. This is point A, this is point A. And this will be the locus of the point B. Yeah. So now when I have uh, 45 with respect to the vertical plane. So 45 with respect to vertical plane, it is seen in the horizontal plane. This is 45 degrees, and this angle will now tell me that all the points B which are at 45 degree, all the points B of the lines which are at 45 degrees with the vertical plane will have this locus. So this is locus of B with 45-degree inclination. This was a locus of B with 30 degrees inclination. And similarly, if I have this angle with respect to the vertical plane and I rotate this, then the projection of this line on the vertical plane is going to rotate in the vertical plane as I rotate this along the cone. So the locus of all points B which are at 45 degrees with respect to the horizontal plane will be a circle with a radius of true length cos 45. So when you are given such a problem, you first, I will just rub this off and I'll now explain the procedure what is done. So so when you draw the first line which is at, so let us say you drew the first line, you located the point A here and you drew a line at 30 degrees whose length was 20 mm. This was 30. So you got one locus of B. This was one locus of B such that all the lines are tilted at 30 degrees with respect to the horizontal plane. Now I want a second locus of B in this vertical plane. That I will get from the 45-degree condition with respect to the vertical plane. So if this is my point A, location of point A in the horizontal plane, I will mark it with red. So now I have that the all the locus of points B which are uh, uh, which are at 45 degrees with the vertical plane, like this is 45. So uh, if I project this here, then the locus of all the points B which are at 45, the locus of point B which are at 45 in the vertical plane is this circle with radius equal to the projection of this line, which is at 45. So here this length is L sine 30, and from here, so this was one locus. This was one locus. Now the second locus is a circle with this length, which is L cos 45. So that's why they draw this line with 30. They get one locus of B. Then to get the second locus of B, they draw the line at 45 degrees. They get the length of the projection of this line here, the length of the projection of line here on the vertical plane. And so here it will be a circle, and uh, so this will be a circle which is the locus of points with 45-degree inclination with respect to VP, and I have a line here which is the locus of all points B, which is at 30 degrees with respect to the HP. So wherever these lines intersect, that is my actual projection of the line. So this was one locus with this as radius L cos 45. I mark it here. And similarly, then the construction says that since you already constructed this at 45, you already have a locus of point B in the horizontal plane. So this is the locus of all points B, which is at 45, which is a constant line, and uh, the locus of point B, which is at 30 degrees with respect to the horizontal plane. So the locus of such points that are 30 degrees is a circle in the vertical plane. So you keep the rounder here, and then you put a arc that has the length of this projection, which is L cos 30. So you put it here and you mark it here or here, wherever. So that will be the projection of your line, and here this will be the projection of your line. So this should actually be in line. So that is how the construction goes. So first you get the locus of point. You need to get the locus of point B once in vertical plane and once in, so it's a line and a circle. One is one is the locus of 30 degrees, one is the locus of 45 degrees. Similarly, in the horizontal plane, you get one locus as a circle and one locus as a line. So let us move on to the next problem, which was also taken in the lectures. So uh, line AB is 80 mm long. So we are given the true length. It makes 45 inclination with the vertical plane. So now this is again the line making an inclination. So it is a true angle. It is a true angle. So true angle, if we have the final projection of a line like this somewhere, so in nowhere, like we saw here or here, we saw that nowhere here, if once I rotate this line, I cannot see the true angles anywhere. In such a figure, I always see the apparent length and the apparent angles. So here when they are saying that they are given true length and this true angle 45, I can only see it in a special case when the line is either parallel to HP or parallel to VP, depending on with respect to what the angle is given. So here they have given that it has 45 inclination with respect to VP. So it is a line like this. So I can see this 45 degrees only when I have this line parallel to the horizontal plane. So, and the next they have given is that front view makes a 55 degrees. So when they say that either front view makes an angle or top view makes an angle, that means that is a apparent angle. So you might remember the dialogue from तारे ज़मीन पर, जो दिखता है वो होता नहीं है और जो होता है वो दिखता नहीं है. So the true angle, that is with respect to HP, we don't see it in the final projection. and whatever we see in the final projection after rotating the line with respect to VP and HP, those are not the true angles. So this front view makes a 55 degrees. So if you say front view, this is the front view. So in front view, you will generally see the angle with respect to HP, but that is not the true angle with respect to HP. But given this information, we can directly say that okay, this is 55, with a note that this cannot be true length unless it is some special case. So uh, if I'll rub this off. So if point A is if point A is 20 above HP, so it will be seen in the vertical plane, and 25 in front of VP, it will be seen in the horizontal plane. So let us mark this point A, 20 above HP here. This is point A, and 25 in front of VP, which will be seen as a distance in the horizontal plane. So this is 25 and this is my point A dash. Now I'm given that this line AB is 80 long and makes 45 inclination with VP. So angle with VP is always seen in HP. So given the true length and the angle of inclination, I can get the locus of point B, which is a line in the horizontal plane, and I can get the locus of point B, which will be a circle in the vertical plane. So once I once I draw once I draw a line at 45 degrees here, making an angle 45, and mark distance 80 this this position is the locus of all points B. Now I can rotate this point B. So what I did is 45 with respect to VP, and they have said that front view makes an angle of 55 with respect to the XY plane. So that definitely means that whatever I'm seeing right now is not the uh, actual projection of the line. This is a special case that I've drawn, but I know that this will be wherever I rotate it, wherever I rotate it, somewhere I'll get somewhere I'll get that the front view makes angle 55. So right now I have made an angle of 45 with respect to VP. So when I rotate this, somewhere I'll get the point B such that all these conditions are satisfied. And this is the second locus of B in the vertical plane. So now the front view makes 55 with the XY plane. So if this is the XY plane, I'll draw a line which makes 55 degrees with the horizontal plane. Now, um, so here this was the actual angle. I know that this is at 45, and from this projection itself, I also got that this is the radius of the circle in vertical plane. So this red circle that I had traced here, that is the radius is 80 cos 45, which I'm going to pick up from here, project it here, and draw a arc which intersects this line which is at 55. So then you get the point B. So this is my actual point B, and this was my sum point, let's say B1, which I drew just to locate the locus of the point B. So now if my original point B, as they have given the conditions, that point B will be actually somewhere here. This will be my actual point B given their conditions. So now they have asked us to draw projections. So we have already drawn the projections. First, we drew the locus of point B in the horizontal plane, given the angle with respect to VP. Then from the same condition, with we also got the second locus, which was in the vertical plane, which was a circle, and to locate the point B in vertical plane, we had another information that the front view makes angle 55. So any line that intersects this circle at 55 will be the point B. So now this is our final projection of the line. This line here, and I projected it here below, and I will be joining this. So this is my AB and this is my AB in top view and front view. So now they have asked find the angle with respect to HP. So now they are asking the true angle with respect to HP. So angle with HP is generally visible in vertical plane. So this 55 is not the true angle. But since we located point B, we now know that any point B which makes a constant angle. So as long as I'm not changing the angle with respect to the horizontal plane, although it is visible as 55 in this current condition, if I want to see the true angle, I'm going to rotate it here like this so that this line becomes parallel to the vertical plane, and only then I'll be able to see the true angle. So when I'm rotating it without changing the angle, I know that this point B is going to trace a line here. So to find the true angle, I know that point B should be along this, and I know the true length. So to find the true angle, I will take the true length in the compass, and I'll make a arc here. So this will be my true length, and my B point is on this line. So B2, let's call this. So A B2 is the true length because that's what I mark, and B I know will always be on this locus. So now if you measure this angle theta, this will be equal to the true angle with respect to HP. So second example that was taken in class was this. So front view of line is 50 degrees inclined to XY. Front view of line is 50 degrees inclined to XY. Now they are saying front view of line. So this means this 50 degrees is the apparent angle. It is not the true angle. So if you have in mind that final drawing that we usually have after rotating the lines with respect to HP and VP, then this apparent angle is visible in the drawing. So this will be 50, and this front view measures 55 mm, while its top view is 60 degrees inclined to the xy. So again, this is the angle that we see here. But are these angles the actual angles? Are these the true angles? No. So always remember that uh, in the final drawing, when the line is inclined to both the planes, we never see the true angle. We only see the apparent angles. And since they have given the angle of front view and top view, we are saying that we can see them in the drawing. So they have said that end A is 10 mm above HP and 15 mm in front of VP. So 10 mm above HP. So the distance with HP is seen in the vertical plane here. So this is my vertical plane. So I've marked A here, and 15 mm in front of VP. So if this is my VP, 15 mm in front of VP, it will be seen, the distance will be seen in the horizontal plane. So I will mark a point A here. So this is the projection of A dash. So I know A, They have said that the front view of the line is 50 degrees inclined to xy. So this is my xy. The 50 degrees inclined line I'll draw, and I'll mark 55 mm to mark B. Now again I have got I have got that this is the locus of all the points B. So when will B trace a line here? Trace a line in vertical plane when it is making a constant angle with respect to the horizontal plane. So this this locus of B making a constant angle with respect to HP. So this is locus of B. And if we are saying that this line is inclined to VP, then and I'm rotating this, then whatever is getting rotated is actually the projected length. So this is angle with respect to VP, and whatever is getting projected, that length remains constant. So the angle with HP is the true angle with HP is theta, let's say, and true angle with VP is phi. Then this line, what is this line equal? The height of this line, the locus of B, it is constant angle with HP line, and the height will be equal to L cos the angle with HP. So this height is L cos theta, and this length this length which is going to rotate here is the projection of the line when the line is inclined to the VP. So the length of this line is L cos, I'm sorry, this should be L, this should be L sine, no, not cos. Oh, this should be L sine theta, and the length of the line which is rotating here is the projection of the line L, which is L cos phi. So length of this line is L cos phi, and this height is L sine theta. So now I've got this front view. So I've got this B, and they're saying that the top view is inclined at 60. So top view, top view is seen in the horizontal plane. So top view is inclined at 60. So let us draw a line at 60. So these are all apparent angles which are actually visible in the figure. So how do I mark this point B now? I will I will project this line here, and that will give me my point B over here. So now I have the final drawing that we used to have after inclining the lines. Okay, so what they have asked for is find the true length. So again same thing. I have this locus of point B. So if I'm rotating it like this is the locus of point B that I just showed you. And when will I see the true length? When while rotating it stops at a point such that this is parallel to the VP, which means that the projection that we see in the horizontal plane, it should be parallel to the XY line. So that's why we rotate A dash B dash. We rotate A dash B dash here. So what we did, right now we were somewhere here, we are rotating it here so that the projection of this line is parallel to the XY, and I know that the B point has it will be projecting a will be tracing a line here. So I've rotated the projection here like this, and now I know that point B should be along this projection, and it should be intersecting this line, because since I'm not changing the angle with respect to the horizontal plane, the height of point B with respect to the horizontal plane, which is seen in the vertical plane, is constant. So now if I join this point A and this point B, this will give me the true length. So I got the true length, and since now again this line is parallel to VP, it is inclined to HP. So whatever angle I see right now here will be my true angle with respect to HP, theta. If I want to see the true angle with respect to VP, so now here true angle with respect to VP, when will I see? When the line is parallel to HP. So what do I need to do? I need to rotate the projection of this line in VP so that it is parallel to XY. So projection of this line in VP is AB. So first we have rotated A dash B dash, which was this rotation. Now I'm going to rotate this AB over here. So I can drop this AB here, and since this is the angle with respect to vertical plane, the point B is going to trace a line in the horizontal plane. So I already knew that this is B dash. So I already had a locus that point B will be along this line, and from this I made the projection parallel to XY. So here wherever it intersects, if I join this A dash and this new point that I got, B double dash, let's say, so that will again be my actually true length, and I will get a angle which is my true angle with VP. Now since here I just realized that we already got the true length, right? So we didn't have to actually project it here and then get it down here and intersect it with this one. What we could have done is uh, since we already had the true length, and I have the locus here, I could just take a rounder, mark the true length, like take this A dash B from here, put the rounder tip here, and cut this cut this locus line, and I would have got the true length, A dash B dash in the horizontal plane. That is, I am rotating here like this, and I would have got the true angle with respect to VP. So whenever you are considering these projection of lines, you have uh, these how many are these? Seven, and there'll be some more, like maybe the location of points or locus of one of the points, like one of the end points of the line. So you have in total four here and four here. So four apparent variables that can be stated in the problem, and four true variables that can be given in the problem. So next we will consider this problem where they have given that top view of a 75 mm long line. So 75 mm long line, that is the true length. Name of line is CD. So top view measures 50 mm. So now top view is the apparent length. So top view will be visible in the horizontal plane. So this is 50. I still don't know the angle. I am just randomly drawing it. So they have said that the end C is 50 mm in front of VP, in front of VP, so that is visible in the HP, so this should be 50. And end D is 50 mm in front of VP. So D का locus ये है and C का locus ये है. So we'll fix C and we'll find the D. So that's it. So they have given the true length. They have given one apparent length, that is the front view, and they have given the location of points. So they have said that C is in HP. So C is in HP, which means that when I see in the vertical plane, I do not see any distance in the vertical plane. So C will be here, and and C will be 50 mm below, in front of the vertical plane. So this is my C dash and this is my C. And they have given that D is 15 mm in front of VP. So I just have a locus of D. I cannot pinpoint D yet. Now they have told us that the top view is 50 mm. Okay. So top view, I can just simply take the distance here and I can mark it here. So top view is the apparent length that we see, that is not the true length, and we can see that in the final projected drawing when the lines are inclined to both the planes. So this was my top view, which was 50 mm. All right. And uh, so this I got top view. So this is actually, when I say that length of top view is 50, it actually means that if my angle with this horizontal plane is some theta, then this top view length is equal to L sine theta. So angle with respect to HP will be seen in VP. So now this this point I located, this is D dash. So I have one locus of D. See, now I'm thinking like, how do I get the D for the vertical plane? So I have one locus of D here which I can project. Where do I get the second locus of D? How will I get the second locus of D which is in the vertical plane? So I can either have a circle, I can either have a circle whose radius I should know, which is equal to the angle between, which is L cos phi. Phi is the angle between vertical plane. So I should either know this radius of the circle so that I can put the point on C and mark the point D, or I should know the uh, or like, if I know this is my angle with the horizontal plane, then I should know that this is the height of point D that I can see in the vertical plane here. So, uh, if I am knowing the true length, if I'm knowing the true length, or even if I don't know the true length actually, I can always say that, wait, I have this angle here. I need to have this distance to be plotted in the vertical plane, right? Hmm. So, so I already have this distance, correct? I already have this distance, which is my vertical distance from the HP. So this is my distance, this is the height of the cone that will always stay constant. No, okay. Even I got confused now. So, ah, okay, yeah. So So to get this locus, actually we'll have to do some construction. So this line C dash D dash, what I see in the top view is actually the projection here, correct? Actually the projection of this line here, which is going to rotate. So if I rotate this and make it parallel to the vertical plane, so like it was initially like this, I made it like this so that the projection is parallel to the vertical plane. Now wherever this, I need this locus. Okay, I don't know this yet. I need this locus. I don't know where the D point is going to come and intersect. So what I'm doing is I'm rotating this projection so that it will come here, parallel to the vertical plane. And in this case, when this is parallel in the front view in the vertical plane, I should be able to see the true length. So that's why, since I know the true length, uh, here I have one locus of the D, and since I know the true length, I will put the rounder here and I mark it there, which intersects this line. So that is how I get the locus of point D here. And now that I get the locus of point D here, then I can join the lines. So this is my point D, which corresponds to the actual projections. And now next they have said that you find the angles with HP and VP. So for the locating this locus itself, we had to draw the true length in vertical plane. So since this is the true length, I already got the angle theta with respect to HP. And if I want the true length with respect to VP, I should I should rotate which thing? I should rotate the projection of this line in vertical plane so that it becomes parallel to the horizontal plane. So projection of the line in vertical plane is CD. So I will rotate it, bring it here. Now this projection has become parallel, and here I already know that the locus is uh, what the locus is here. So if I join this thing, this projection and this locus of D, I will get this as true length, and this will be my true angle phi with respect to VP. Or else again, like last time, we already had true length, so you actually need not have to do all these constructions. You just take C dash, take the pointer at C dash, simply mark the take the true length in rounder, mark it at D dash, and that will give you the actual angle phi. This will be phi or this will be phi. So that is the angle with respect to the vertical plane. Okay, so this one is the last example for today. So this one was actually an interesting problem that professor took in the class. So there are two straight lines PQ and QR making an angle of 120 between them in front view and top view. So again, this 120 degrees is actually the apparent angle in front view and top view. So you can actually see the angle in front view and top view. This 120 and 120 in top view, but this is not the actual angle. Now they have said that PQ is 60 mm long. 60 mm long, it is parallel to HP and VP. So if this is my vertical plane and this is my horizontal plane, this line is going to be parallel here as well as parallel here, and have said that distance from both the planes is 15 15. So the projection of such a line is always we always get the true length. So we can directly draw PQ here and PQ here. Length will be 60 and this distance will be 15 mm. Now they have said that determine the true angle between PQ and QR given that the point R is 50 mm above HP. So this was my Q point, this was 15 and this will be 50. So now what they're saying is we have some lines which are like this inclined and they're somehow inclined. Okay, so the projection of this line in front view shows that it has 120 angle and the projection in top view says that it has angle 120, but that is not the actual angle, which so that is what they are asking you to find. Now you see the actual angle only in the plane which will pass through both of these lines. So uh, so either you try to rotate it like this so that the plane in which both these lines are there will be the vertical plane. So if you imagine like this line, now imagine that this is my vertical plane and this is my horizontal plane and this is my line here, somewhere like this. So if I want to rotate it like this is not going to change because this is already parallel to HP and VP. This is my vertical plane, horizontal plane. What will change is this. So since I'm not changing the angle with respect to this line, I'm not changing the angle of QR with respect to this PQ. If I rotate this line, what does it say? This R point will be at the same distance like this. So if I have R over here, however I rotate it, that R point should always be along along this line. So R is always going to be along this line wherever I rotate it. Why am I rotating it? Because I want the plane which contains both these lines to be the vertical plane. So that's why I'm trying to rotate this. So one locus of so when I'm rotating, how do I change the R? The height will change because if you have a cone like this and I'm rotating it like this, right? So the so consider that this is my this string is my QR. This string is my QR. So when I'm rotating it, if you see in the camera, you will see that this point the height is changing, but this plane will always remain the same, which I see as a line. So R will always move on this line, but the height will change. Now another thing you need to note is when you see it in the plane where you can see the true angle, you will also see the true length of this line. So now we don't know the true length of QR. We know the length of PQ, but we don't know the length of QR. So what if you knew the length of QR? Only thing you need to do is you rotate it, and to construct the point R, you will put the rounder here and put a arc here such that this length is the true length. But you don't know the true length. So how do you find the true length? So for that, if this is QR, I know that wait, so this is Q, right? And I know that QR makes angle 120. So I already have this angle, and since I marked this, I also have this R dash here. Okay. So this R dash that is projected in the horizontal plane, it is the projection of this line in the horizontal plane. So if I want to see the true length, I will rotate I will rotate this projection so that it becomes parallel to the vertical plane. Or otherwise I can rotate this R also here, and I know the locus. So this is one locus, this was one locus. I'll join this, I'll get the true length. Or else I can rotate q dash r dash here. I'll get this as locus, and I know that r is here. Yeah, so here why anyway you can find the true length whichever you feel comfortable. So here I rotated this, I went up, and this is my second locus of r. So I get this as true length. So anyhow you can get the true length, and once you get the true length, then you can mark it on the original r line that was there, because if you rotate it like this point r is always going to be in the same line. But the only thing you need is that this should be the true length. So you found the true length by rotating the projections, and then you took that true length and you marked it on the straight line where the r should be. And then now this is, since you see the true length, you will also see the true angle between the lines. So we can cover this plane thing maybe next time, or okay, I'll just finish it this time. So let us consider this plane. This is the plane. This is, let's say, 80 mm, and this is 60 mm. So I can see the true length only when the plane is either parallel to the horizontal plane or parallel to the vertical plane. So let us assume we can see it in the horizontal plane. So we will see the exact dimensions here. So let us say these are the dimensions A, B, C, D, which I see here. So in the horizontal plane, I will see the actual exact dimensions. In the vertical plane, I will see the only the line, because these lines, this line will get down to a point, this line will be seen as a point in the vertical plane, and these two lines will be seen as one line and not two lines. Now what they are saying that we are rotating the plane by 30 degrees with respect to the horizontal plane. So I rotated it like this. Now the angle with respect to the horizontal plane is seen in the, so my vertical plane is here. This is my horizontal plane, vertical plane is here, sorry. So the angle with the horizontal plane will be seen in the vertical plane. So but the length does not change. So this is as good as saying I had a pencil here, and this is my vertical plane, this is my horizontal plane. I made an angle with respect to the horizontal plane, so this is 30 degrees, which I am able to see in the vertical plane. So since this line is still parallel to vertical plane, I see the true length. So even in this length does not change. I just rotate this to 30 degrees. And then this was my AB and CD. So initially I was able to see AB here and CD here. Now I just did this. So I can see AB here and CD here. And when I project it down, here I will see a shorter rectangle like this. Now they have said that they have rotated it around a point by 45. So there is a difference in rotating it with respect to a plane and a point. So here now, if you want that you are rotating this whole surface along a whole surface such that it makes 45 with the vertical plane, then you will have to rotate it along this line, this edge. But they have done a simple case where they are rotating this line like this. Okay, so when you do this, only the projection in the top plane gets tilted like this here. So first I did this, and then I just rotated it like this. So when I rotate it like this, I'm not doing anything. My inclination with respect to horizontal plane is same. So just imagine that this line is this pencil. So my inclination with the horizontal plane is this, and now I'm trying to rotate it like this. So my inclination, like this elevation, does not change in the vertical plane. So that's why uh, we can project it here, because I did not change the elevation. I kept it at 30 degrees and rotated it simply. So the height of these points is same and these points is also same. So AB will always be here on this line and CD will always be here. But now that I've rotated it like this, uh, I have drawn the tilted rectangle. So A and B both are here on at this height. So I will project A here. I will project B also till here. And since I've rotated it like this, but my heights are still same, so my C will be extended till here and D will also get extended till here, and that is how we get the parallelogram. Now, if you go to a difficult case where you are rotating it like this, and then you are rotating such that, so if you're rotating it like this, if you see this plane, this is the vertical plane. This plane is still making a 90 degrees with respect to the vertical plane, just that I have you can imagine that the horizontal plane is rotating. So if put a condition that I want this surface instead of a line, if I want this surface to make a 45 with the vertical plane, then you can imagine a lot of points change. And if you want this whole surface to make an angle with the vertical plane, then you need to rotate around the axis, which is some edge of this uh, rectangle. Whereas when you were rotating around a line, the axis of rotation was either perpendicular to the horizontal plane or perpendicular to the vertical plane. That is a easy case. Why? Because you are not changing the elevation of the points. So you can simply extrude these points here and get the elevation. Only thing you change is this rectangle in the top view. But once you say that you want to tilt the whole surface by 30 degrees or 45 with respect to VP, then you need to rotate it. Already it is like this, so you need to rotate it along this. So if you rotate it, these points are not going to be at the same height. They'll go like this. So for that, you generally go for auxiliary planes. You take projection on the auxiliary plane and then come back and do many more things. So maybe we'll cover that in the next live class.